To build any software-defined embedded system, it's very obvious that you need software, you need hardware, and also development tools to put the software and hardware together. But today's software-defined embedded systems are very complex, and they need to be safe and secure. So you need an efficient tools to put them together, and these embedded robotic systems have to safely communicate with each other. So for those reasons, we have QNX General Embedded Development Platform, and if you see here, we provide not only just the OS and the hypervisor, we provide the entire software framework and also a starting application so that you can accelerate the building of your software-defined embedded system. So in this particular thing, the only software component that's tied to the hardware is the board support package and also the drivers here. And our software runs in an x86 processor or an ARM processor, and it can run on the cloud or in the production hardware. So you don't need to wait so that for your development of your software, for building your device, you can start off on any hardware, and because most of the software above this board support package is completely software defined, you should be able to migrate from one system to the other. We also provide a jumpstart application. When I say jumpstart application, a starting application is a hello world application, and we have the virtual factory demo that is also a jumpstart application for us to build robotics. Let me show some of the middleware components we have here. We have the sensor framework, which is used to connect the cameras, the LiDARs, radars. It can be used for autonomous applications, autonomous functionality. And we have different frameworks for user interfaces. We are going to see more about that in the demo. We have rich user interfaces, 3D augmented reality, which we are showcasing there. And the other framework here is the security framework. Every device needs to have a birth certificate, and we provide a birth certificate to the extent you can. Every subsystem can be authenticated to, and along with it, we can have code signing, which can be quantum resistant too, so that it cannot break by quantum computers. And we also have a software-defined audio, so that whenever you have audio, you can have a system-level audio development that you can do. Audio seems is a necessary component that when you're building humanoids, it can be also used not only for your sound, but also can be used for sensing applications. In one of the humanoid robots I've seen, they are planning to use more than 16 microphones, because microphones are omnidirectional. You can do that for sensing different kinds of sensing applications. So with this particular, we support a lot of open source components too, like ROS2, like KDL, which is a inverse kinematics for robotic systems. There are several open source components we support, and the software itself is POSIX compliant and open. But the quick takeaway is, you have most of the software. It's a platform that is given so that you can accelerate the building of these devices. So let's go and see. And these are the development tools we talked about. We provide pre-certified software. When we say pre-certified software, you can show this as an evidence when you are certifying your whole system. And using this approach, you can save more than a year or up to 18 months of certification efforts. Shall we go and see the demo? Okay, Matt. So we've seen the stack there, General Embedded Development Platform, which accelerates the building of your software-defined robotics or software-defined embedded systems for any industry. And we also said that we provide not only the foundational components, safety certified components, but we also provide a starting application so that you can start off from that applications to build your own innovative product. So this is an example of such particular starting applications called the virtual factory demo. What we are showcasing is QNX is running on this single Intel box, which has got on the single multi-core SoC, which is a 12-core here. And what we are doing is, and the bottom box that you have here is a robotic controller. That robotic controller is just a black box here in this case, which actually is controlling the 7 degrees of freedom that this robotic arm has. That means there are 7 motors here that are running here. So, and all the application, that the use case that needs to be done is running on that single embedded Intel box. So what are we running here? We are running the Unity 3D. This entire virtual factory demo is running on that particular one single SoC. Not only that, we are showing a digital twin of this particular robotic arm. And if you see, this is the space mouse we have here, the mouse to move it. And you can see in real time, it's almost very realistic model. There's no camera here. So we have a 3D model running natively on a hard real-time operating system, which has got a very ultra low latency timing requirements. Like that means in some of these robotics, you need to have feedbacks, because these robots, when they interact with the human beings without any fences or guardrails, they need to have a force feedback. That means immediately you feel any force that it's trying to crush or something, it has to stop by itself. For that reason, this has to be continuously monitored. So our software is able to continuously monitor that. Otherwise this robotic arm will not function. Okay, that is one main thing. While doing that high-speed operations of monitoring for the force feedback for safety, it is also doing the Unity 3D on the same thing. So you can also, now that you have a multi-core SoC, you can have the safety controller. You see here the stop button here. In a typical factory, you have a safety controller externally on an assembly line, and if something goes wrong from different machines, it automatically stops the assembly line. But now, with the ability to do hardware consolidation, do many things as a software defined on the same single SoC, you can actually have that safety controller also running on the same box. So no more need to actually have those wires moving everywhere. If you have introduced a new industrial controller, you need to draw a new line again back to that safety controller. But now when you software define this safety controller, you can actually have a software defined signal itself as your new adaptable assembly line. So it accelerates innovation for you. So we are running Unity, and what else we are doing? We are having this Aruco, augmented reality tagged based things. Each tag is marked as red, green or blue. And if you see here, in real time, we have a camera here. In real time, we are able to see this, and we use an open source component called OpenCV. And based on this, we are painting that green square on the screen. And this demo, I can even maybe, let's say, show you, zoom it up. Is it getting lengthier for you, or is that okay? And the other thing is, other feature of this is, you also have a hypervisor running on the same system. So with that, we are running a Ubuntu guest here. This is an Ubuntu guest. It is called RVIS. It is a ROS visualizer. ROS is a communication that is open source communication that is used to, is based on a publish subscribe interface protocol, so that you can send commands to control and manage the robotic systems. It's not only seeing the native camera vision, we also can send that command again, and we can also visualize in the RVIS world too. The fact here is, like, we are running the hypervisor, running a Linux guest running on top of a QNX based system. And other aspect of it is the mixed reality aspect of it. If you see that you have a blue, red and a green zone here, but that blue, red and green zone are not in the physical world. So you can use like your space mouse here. The space mouse is sending the commands to the robotic controller, and those commands are used to place your object that it is being seen. This is a virtual cube is actually being placed in those zones, and for the gamification purpose, when the cubes are placed, the colored cubes are placed in the proper zones. The yellow cube starts on those 3 conveyor belts. Once it starts, we are just showing here the amount of processing that you can do. And this is a gamification part of it, and now this is a virtual robot, complete virtual robot. It's nothing, we detached it from the physical robot. So the significance of it is, you don't even need to have this expensive physical robot to start your application. You can actually start with that because the command that you send to the robot or robotic arm or this physical robot is the same. It does not matter. Once you get your application, everything working there, you should be able to put it here and everything works, so there will be no surprises at all. And that virtual robot, now that this one is running on this particular target itself here, locally here, but I can get a digital twin of the same thing running in the cloud, so that you can have any number of those virtual robots or digital twins of the robotic arms, and you can have distributed teams working on it. And anytime your code is checked in, each time you can get a degree of quality of your code before even you try it on the physical hardware, which is really very expensive. So the simulation first world, we are already there. This is an example of simulation first before you can get it. So it enables to accelerate the building of your devices. And yeah, that's in a nutshell. Something in detail, but if you have any questions, yeah, please feel free, Matt. Yeah, hopefully this will help.
That was awesome.